Topic 2, Mechanics of Forces, Translational Equilibrium. Mostly Newton's first law.
And second law.
An object of mass m is hanging via three cords as shown. Find tension in each of the three cords in terms of mass. Give each tension a name to organize your effort. T1, tension 1, tension 2, tension 3. Draw a free body diagram of the mass and the knot. So for mass, the mg is downward and tension 3 is upward. As the object in translational equilibrium, the net force equals to 0, so T3 equals to mg. Now we break T1 and T2 down to components. Looking at the free body diagram of the knot, we see that T1 in x component is adjacent, so T1 times cosine 30 degree, which is equals to 0.866 T1. Y component of T1 is opposite, so T1 times sine 30 degree, which is equals to 0.5 T1. T2 x component is adjacent, that is T2 cosine 45 degree. That's equals to 0.707 T2. T2 and y component is opposite, so T2 sine 45 degree. That gives us 0.707 T2. As the object is translational equilibrium, resultant force in x component equals to 0. 0.707 T2 minus 0.866 T1 equals to 0. And T2 equals to 1.225 T1. Similarly, as the object is translational equilibrium, resultant force in y component equals to 0. 0.707 T2 plus 0.5 T1 minus T3 equals to 0. Substitute equation 1 into equation 2. We get this one, and substitute T3 equals to mg into the last equation. And T1 equals to mg over 1.366. Now substitute T1 into the first equation. We get T2 equals to 1.225 mg over 1.366. And that gives us T2 equals to 0.897 mg. 25 kilogram of mass is hanging via three cords as shown. Find the tension in each of the three cords in newtons. And now the mass is given, we just substitute the three equation we just derived. T3 is 250 Newton, T1 is equal to 180 Newton, and T2 is 220 Newton. A 1,000 kilogram aeroplane is flying at a constant velocity of 125 meters per second. Label and determine the values of weight and the lift, the drag, and the thrust if the drag is 25,000 Newton. Since the velocity is constant, Newton's first law applies. The resultant force in x component equals to 0, and the resultant force in y component equals to 0. W equals to mg, and mass is 1,000, and for g, let us use 10. That gives us 10,000 Newton downward. Since the resultant force in y component equals to 0, lift force minus the weight equals to 0. So lift force equals to weight, which is 10,000 Newton upward. Drag force is 25,000 Newton, tries to impede the aircraft to the left. Since the resultant force in x component equals to 0, thrust minus the drag force equals to 0. Therefore, thrust equals to drag force, which is equals to 25,000 Newton to the right. And we have our free body diagram. Newton's second law, if the sum of the forces is not 0, the velocity will change. Newton knew that the change in velocity is an acceleration. So Newton then asked himself, how is the sum of the force related to the acceleration? The acceleration of an object is proportional to the net force acting on it and inversely proportional to its mass. So we have our equation, net force equal to mass times acceleration. Looking at the formula, resultant force equals to ma, note that if acceleration equals to 0, then resultant force equals to 0. But if acceleration equals to 0, then velocity becomes constant. Thus, Newton's first law is just a special case of his second law, namely, when the acceleration is 0. Let's take a look at the example. An object has a mass of 25 kilogram, a tension of 50 Newton, and a friction force of 30 Newton are acting on it as shown. What is its acceleration? The vertical force W and R are cancelled out as object moving horizontally. The net force is tension 50 Newton minus a friction force 30 Newton, and that resultant force is 20 Newton to the right. We apply F net equals to ma, net force is 20 Newton, mass is 25, acceleration is 0.8 meter per second per second. A 1,000 kilogram aircraft is flying in perfectly level flight. The drag D is 25,000 Newton and the thrust is 40,000 Newton. Find its acceleration. Since the flight is level, so resultant force in y component equals to 0. So the plane is not moving up and down. It's flying perfectly level flight. So lift force and weight cancel out. Resultant force in x component, thrust 40,000 minus the drag force 25,000, that gives us 15,000 Newton. So our net force is 15,000 Newton. Apply Newton's second law formula. F net equals to ma. F net is 15,000 Newton and mass is 1,000 kilogram. Acceleration is 15 meter per second per second. Example, a 25 kilogram object has exactly two forces. F1 equals to 40 Newton and F2 equals to 30 Newton applied simultaneously to it. What is the object's acceleration? Resolve F1 into its component. Adjacent, 40 cosine 25 degree is 36 Newton. Opposite, sine 40 times sine 25 degree, that gives us 17 Newton. F net in the x component, we have only 36 Newton. F net y component, we have 17 Newton upward plus the 30 Newton upward, that gives us 47 Newton. So F net squared equals to F net x squared plus F net y squared. F net squared equals to 36 squared plus 47 squared, and F net equals to 59 Newton. Then from F equal to ma, F net equals to 59 Newton. Mass is 25 kilogram. Acceleration equals to 2.4 meter per second per second. A 25 kilogram object resting on a frictionless incline is released. What is its acceleration? Begin with a free body diagram. Weight is downward. Normal force is perpendicular to the surface. Break down the weight into its component, and the angle is 30 degree. Y component is adjacent, mg cosine 30 degree. X component is opposite, mg sine 30 degree. As it is frictionless surface, so no friction is acting on it. We can move the vector around in a parallel manner. Since r and mg cosine 30 degree are perpendicular to the path of the crate, they do not contribute to its acceleration, so they cancel out. Therefore, F net equals to mg sine 30 degree, which is equals to ma. M's are cancel out. Acceleration equals to acceleration due to gravity, g, in this case 10, times sine 30 degree, which gives us 5 meter per second per second. What is its speed at the bottom? We found that its acceleration is 5 meters per second parallel to the surface. We don't know the time. Let us use the timeless formula. V squared equals to U squared plus 2AS. To find final velocity, we need the displacement, S. We have opposite and we want hypotenuse, S. So from trigonometry, we use sine theta, which is opposite our hypotenuse. Opposite is 6 meters. And hypotenuse is the one we're looking for, displacement, S. So S equals to opposite our sine theta, which is equal to 6 over sine 30 degree, which is equal to 12 meters. Now let's plug in. Initially, the object at rest, initial velocity is 0, plus 2 times acceleration is 5, displacement is 12. That gives us 120. And both sides squared, we get final velocity 11 meters per second. 100 Newton crate is to be dragged across a floor by applied force F equal to 60 Newton, as shown. The coefficient of static and dynamic frictions are given, 0.75 and 0.6 respectively. What is the acceleration of the crate? Let us draw a free body diagram. mg downwards, normal force is perpendicular to the surface. F drag is 30 degrees to the horizontal, and the friction is opposed motion. Static friction will oppose applied force until it is overcome. Determine if the crate even moves. Let's find the maximum value of the static friction in red and compare it to the horizontal applied force F cosine 30 degrees. If horizontal applied force is larger than the friction, then object move. Applied force is 60 times the cosine 30 degrees gives us 51.96 Newton. The maximum static friction force is, based on our data booklets, maximum static friction equals to coefficient of static friction times R. And coefficient of static friction is 0.75 times R. We need to find R. Since the object is moving horizontally, the vertical component of the resultant force equals to 0. And Y component of the applied force is F sine 30 degrees, as it is opposite. So upward direction R plus the F times sine 30 degrees minus the weight mg. R plus 60 sine 30 degrees minus mass is 10. Acceleration due to gravity, we use 10. That's 100 equals to 0. R equals to 70. Plugs R into maximum static friction formula. Coefficient of static friction 0.75 times R, normal force is 70. That gives us 52.5 Newton. Maximum static friction 52.5 Newton, larger than the horizontal applied force F cosine 30 degrees, 51.96. Therefore, we conclude that crate will not even begin to move. If someone gives a crate a small push of how much, it will break loose. What will its acceleration be then? Solution: horizontal applied force is still adjacent, F times cosine 30 degrees. That is 51.96 Newton, same as before. The dynamic friction force is Fd equals to, now we need to use coefficient of dynamic friction times R equals to 0.60 times R. So reaction force is still R equals to 70. We derived this before. Let's do that again. As the object moving horizontally, the vertical component of resultant force equals to 0. R plus F times sine 30 degrees minus mg equals to 0. Let us substitute values. R plus 60 sine 30 degree minus mass is 10. With acceleration due to gravity, we use 10 equals to 0, and R equals to 70 Newton. And the dynamic friction equals to 42 Newton. Dynamic friction, 40 Newton, is smaller than horizontal applied force, F cosine theta, 51.96. Therefore, the crate accelerates. Net force, horizontal applied force, F cosine 30 degree, minus the dynamic friction equals to ma. As the object is accelerating horizontally. So F times cosine theta is the horizontal component of applied force minus the friction opposite direction. That gives us ma. F cosine 30 degree is 51.96 minus dynamic friction 42 equals to mass is 100/10, which is 10 kilogram, and acceleration equals to 0.996 meter per second per second. Newton's law of motion, Newton's third law. For every action force, there is an equal and opposite reaction force. The symbol FAB equals to minus FBA. That is, force on body A by body B is equal, opposite direction to the force on body B by body A. In the big picture, for every force in the universe has a reaction force that is equal and opposite. The sum of all the force in the whole universe is 0. So why are these accelerations all around us? Because each force of reaction pair acts on a different masses. Let's take a look at this interesting example. When you push on a door with 10 Newton, the door pushes you back with exactly same 10 Newton, but in opposite direction. Why does the door move and you don't? Even though the forces are equal and opposite, they are acting on different bodies. Each body acts on response only to force acting on it. The door can't resist, but you can resist.